Imagine a flock of birds searching for food. No one leader directs them, yet they move in harmony, adapting and learning from each other to find the best solution to their shared goal. What if we could mimic this natural phenomenon to solve complex problems in science, engineering, and technology? Hi, and welcome to Premature Abstraction. Today we are taking a look at the particle swarm optimization algorithm. Let's find another analogy to derive the core idea behind the algorithm. Imagine you're out in a field with your friends. All of you are equipped with a phone which you can use to talk to each other and which tells you the position and altitude via GPS. Oh, and also you're blindfolded. Okay, I'll admit that the analogy may be a bit far-fetched, but bear with me. Now, your goal is to find and meet at the highest hill in a large landscape. What would you do? Probably all of you would first start in different locations so that you cover most of the area and don't miss a big region. And then everyone would just walk in a random direction. If you found a better spot, you would write it down and explore a bit more into that region. Then, from time to time, you would coordinate who of you has found the highest spot yet, and everyone would walk a bit into that direction. The farther away you are, the faster you would go. And that is actually already the whole idea behind PSO. So let's formulate it concretely. But first, a small adjustment. In the literature, the optimization goal more often is the minimum of the objective function, instead of the highest peak. Also, another disclaimer. When algorithms are rigorously explained, there are often iteration variables and indices thrown around to keep mathematical accuracy. However, in this brief explanation video, I would like to keep it simple and just explain what shapes the mentioned objects have. The rest then follows from that. Luckily, modern programming languages, like Python, automatically handle distribution of various array shapes, so we will be able to implement this algorithm almost exactly the same way. You'll see an example implementation later. As an input, our algorithm takes the objective function that we want to minimize. The function can have real inputs in any dimension, let's call it D, but only a one-dimensional output, which makes sense. Otherwise, we would not even be able to say what maximum or minimum even means. We select a search range S and a fixed number of particles n. First, we initialize all the positions x of the particles as random in the search space and the velocities of the particles v in random directions. Furthermore, we build a list P, which we use to note down the best position that each particle has found yet. Let's call them the local minima. At the beginning, this is of course the current position. Let's get on one page what the current shapes of our arrays here are. All of them have the same shape, so let's take X as an example. We have a collection of n position vectors that each have d dimensions, so we can store this as an n by d matrix. Alright, let's continue. Next, we will look for the best global minimum that has been found yet. We'll call it p hat. So for all the local minima, find the one with the lowest value when applying the function. This is usually denoted as argmin. That is all the initialization we need. Next, we start the simulation of the particles. Similar to how one would write a physics simulation, we simply add the current velocity vector to the positional vector for each particle. This is then the new position. In each iteration, we also update the velocities, and this is commonly done beforehand. You can think of this like acceleration in physics. First, each particle strives towards its local minimum. Simple vector arithmetic gives us this term to add to the velocity. And then each particle is also attracted to the global minimum, giving us this term. The only thing left is that each particle updates its yet best found location, and from that, all particles agree on the overall best position yet, the global minimum. After all iterations, we return the global minimum as the found solution. Now, if we left it at that, there would be a high chance that the particles agree too soon on a non-global optimum. Instead, we want to introduce some randomness, a vector between 0 and 1 that randomly controls the influence of the minima in each iteration. This way, the search space is explored more. Last, we want to be able to tune the algorithm, so we introduce some hyperparameters. Like I already mentioned, we exchange some details for clarity in the equation, so let's state the dimensions of our variables here again. We already know x, v, and p are n by d matrices. The same goes for the two r's. The global minimum is a d-dimensional vector, and our four hyperparameters are just plain scalars. If you want to test it out yourself, here you can see a simple implementation of the algorithm in Python using NumPy. Note that this implementation is quite inefficient, as it evaluates the objective function multiple times for the same input values. This can additionally be optimized by caching values or rearranging the code. Finally, let's watch how a swarm searches for the minimum of an objective function while varying the hyperparameters a bit. As you can see, the swarm is not guaranteed to converge, and sometimes some particles get stuck because of local minima. We want to get a feeling about how the hyperparameters influence the swarm behavior. Let's start with A, which is the parameter that decides how much of the velocity is kept from the previous iteration. Therefore, it's often called the inertia weight or momentum factor. It can be thought of as a dampening parameter. We know that this parameter should be smaller than 1, otherwise the particles would accelerate more and more. If we choose something smaller than 0, we have an interesting effect, where each particle jitters back and forth. That's because in each iteration the velocity gets flipped in the opposite direction. But if it's not less than -1, it still looks like it can converge. The two B's dictate how much the particles should be pushed towards the local and global minima. That's why they are called the cognitive and social coefficients. For both, only positive values make sense. Otherwise, we would drive the particles away from their already found optima. When we choose different values for the two parameters, we can tune whether we want to put more weight on each particle's local optimum or whether we want to nudge them all to the global one. If both are similar, this can lead to particles not being able to decide whether they should go to the global or their local minimum. Last, we have the parameter C that controls how much of the velocity update should be added to the current position. It's kind of like controlling the aggressiveness of convergence. One can compare it to the learning rate in gradient descent. Small values lead to more considerate steps but take longer to converge, or even converge into local minima, and large values may lead to skipping over minima. Of course, it should also be chosen positive. Let's have a more rigorous look at the way the particles may converge. First, let's make a huge simplification, namely that every dimension is decoupled from another. This primarily means that we can have a look at the convergence for each dimension independently, so we will only look at the one-dimensional case. For that, let's focus on the two movement equations. Because we have the random factors, this algorithm is still stochastic. We will transform it into a deterministic one by setting both r's to their mean, which is 1/2. Also, we can find this substitution here, which leads to this nice formulation of the algorithm. You can pause here and check, or just believe me. The substitutions also have some intuitive interpretations. For b, we simply take the average of the two b's, so the average coefficient for the local and global attractor. And for p, we take a weighted average of the two, weighted by the corresponding b's, which gives us the average attraction point when taking into account the attraction coefficients. With some clever transformations, we can eliminate v entirely from the equation. Here we see something interesting. b and c only appear as a pair. That means we can make our calculation easier by setting c to 1 without any loss of generality. Okay, and why did we do all of this work? Because now we can write our substituted movement equations in matrix notation. Again, you can pause and check if you want to. By the way, from now I omit the bars above b and p, as it should be clear what is meant. In the context of dynamic system theory, this has a nice interpretation. Y is the current state of the particle which gets updated each step. A is the dynamic matrix from which we can derive the behavior over time of the particle. P is the external input in this interpretation. The particle will be driven towards that. And B is called the input matrix, which controls the effect of the external inputs on the particle state. From that, we can firstly derive the equilibrium point, so the point where the system does not change anymore when the input is not changing. In other words, when yk plus 1 equals yk. We can easily solve this to p0, so when the position is p and the velocity is 0, we have an equilibrium, which is actually not that surprising but reassuring that we could mathematically derive that from the equations. Next, we can examine the convergence behavior. Now, depending on your background, this may come a bit out of the blue, but we can derive the time behavior by looking at the eigenvalues of the dynamic matrix A, which are the solutions to the following equation. When both eigenvalues have a magnitude less than 1, the system will eventually converge. This is exactly the case when the following conditions are met. We can visualize them as this. So as long as A and B land in this triangle, the particles will converge, no matter the initial position and velocity. Additionally, when the two eigenvalues are complex, we will see harmonic oscillations. This is equivalent to the following condition. Again, we can visualize it like this. So if the parameters fall inside of this area, they will oscillate around the equilibrium. Last, it is possible to produce a zigzagging behavior. That happens when the real component of at least one of the eigenvalues is negative. This condition here is equivalent, and we visualize it as this area here. We can lay all of them on top of each other and see that we can find all combinations of those three behaviors. Let's go through them. First, given that we want the particles to converge, we have oscillatory behavior without zigzagging. Oscillatory behavior with zigzagging. No oscillatory behavior with zigzagging. The zigzagging can be symmetric or asymmetric. And no oscillatory behavior without zigzagging. When not converging, we can again have those four cases, although they are not very interesting because of the diverging behavior. There is one important thing we did not mention yet. Given our assumptions, the particles are guaranteed to converge, but only to the global attractor P. Of course, this does not need to be the global or even a local minimum of the actual objective function. That's why it's so important to have the randomness terms in the equation, so the particles cover more space in their exploration. One thing we did not talk about yet are convergence criteria in practice, because in the way we currently implemented it, it will run forever. So we need to think of some kind of stopping criterion. Depending on the application, these are the most common ones. First, we could simply run for a fixed amount of iterations. Surely, we can only use this method if we have good reason to believe that the particles won't make any progress anymore after a specific time. Next, we could keep track of how frequently the global optimum is updated. And when it takes the swarm a long time to find an even better solution, we stop. Another idea would be to measure the radius of the swarm, so the distance between the two most distant particles, and stop when it is sufficiently small. However, this can be very expensive to compute, and depending on the function, it may actually not reach the criterion if half of the particles are stuck in a local minimum. Also, we could stop when the sum of velocities approaches zero, so when no particle significantly moves anymore. Since we add random acceleration to the velocities, this can also be suboptimal, depending on the hyperparameters. Basically, all of them have advantages and disadvantages, so you really need to decide which fits best for a given problem. Alright, we have seen all of PSO's behaviour, and maybe I have already convinced you of its beauty, but we did not talk about whether it's a good idea to use it yet. Let's talk first about the advantages. There is no derivative needed for PSO. This is very important because for a lot of problems there is no derivative available. Also, this means that the convergence behaviour is not affected by the derivative in case the function is differentiable anyway. If we look, for example, at gradient descent, we actually need to set our learning rate in coordination with the gradient. When we scale the function, and therefore also the gradient, we must divide the learning rate by that factor to have the same convergence behaviour. Whereas for PSO, it's always the same. So there is no derivative needed, but in fact the function does not even need to be continuous. Of course, there are some wild functions one can construct where PSO then also has a hard time. But generally, since each particle is only attracted to their local and global minima, it does not matter how big of a mountain is in between, or if that mountain is continuous. This is, for example, a major limitation of most gradient-based learning algorithms. It can also handle noisy functions well. Until now, we always looked at more or less smooth surfaces where we want to optimize. But PSO can be deployed in completely different scenarios, such as different neighborhood topologies or discrete spaces. Other algorithms often start with one initial value, and it is easy to make a poor choice here. In PSO, many different starting positions are chosen and automatically coordinated, that the best of them is taken. The algorithm is very easy to parallelize or even distribute onto multiple machines. Each particle can do most of the work on its own, and then there is only the communication step where they need to coordinate. Let's imagine an objective function that is very time-consuming to compute. For example, when we want to find the best hyperparameters when training a deep neural network. For every position in our search space, we need to train a whole neural network, which can quickly take days. We can simply distribute the load to multiple machines, for example, one particle per machine. In this paper, the researchers showed that this optimization technique can compete with the state-of-the-art in hyperparameter optimization. There are, of course, many other applications of PSO. Because it has so few requirements, it can be applied to optimization problems in many fields. A few examples are cancer classification and diagnosis, quality control for crops in agriculture, optimizing chip placement in circuits, finding optimal locations for electric vehicle charging stations, malware detection, the job shop scheduling problem and task scheduling in cloud computing. So you can see the applications are mostly limited by your imagination. Of course, there are also some downsides to PSO. The whole algorithm depends on the occurrence that a particle crosses the global optimum more or less by chance. Some even degrade PSO to just being fancy grid search. For many optimization problems like convex optimization, there are much more elegant ways of finding the guaranteed optimum. You need to roughly know where to look, although this is often a prerequisite for optimization algorithms in general. Not needing the derivative is a nice precondition, but in most real-world problems you either have the derivative or it is sufficient to approximate it. This is exacerbated for high-dimensional problems, where the guidance of the gradient can be helpful. That's one of the reasons why deep learning with gradient descent is so successful, but of course it also struggles with high dimensionality at some point. If you don't utilize its high ability to be parallelized, it can be unnecessarily costly to compute, especially when using many particles. In conclusion, I think it is safe to say that PSO definitely has its place in a toolbox for optimization. Nowadays, machine learning and optimization is mostly about deep learning, And it's a shame because those intuitive algorithms fall under the rug. But if we take another look at methods like PSO, we might find they're not just clever, but also surprisingly practical and easy to work with. It's a reminder that sometimes the old school approaches can still deliver. This has been Premature Abstraction. Thank you for watching.